Hello everyone. Thanks to everyone for watching this video. My name is Qi Da. I am an architect and engineer. Today's video is titled Implant Bending of Beams, and it is going to provide you a broad overview of beam bending and also the analysis of beams. I am going to give you an overview of what I am covering today's video. First at all, we will have a look at some fundamentals of the implant bending of beams, then move on to the elastic and plastic analysis, then wrap up with conclusions. Beams are structural members which transfer the transverse loads they carry to the supports by bending and shear actions. Beams generally develop higher stresses than axially loaded members with similar loads, while the bending deflections are much higher. These loading deflections of a beam are often, therefore, a primary design consideration. On the other hand, most beams have small shear deflections, and these are usually neglected. The strength of a steel beam in the plane of loading depends on its section properties and on its yield stress Fy. When bending predominates in a determinate beam, the effective ultimate strength is reached when the most highly stressed cross-section becomes fully yielded so that it forms a plastic hinge. The moment MP at which this occurs is somewhat higher than the first yield moment My at which elastic behavior nominally ceases, as shown in this figure. In this video, for the sake of simplicity, static determinate beams will be focused on. Next, we will introduce the elastic analysis of beams. The design of a steel beam is often preceded by an elastic analysis of the bending of the beam. One purpose of such an analysis is to determine the bending moment and shear force distributions throughout the beam, so that the maximum bending moments and shear forces can be found, and compare with the moment and shear capacities of the beam. The data required for an elastic analysis includes both the distribution and the magnitudes of the applied loads and the geometry of the beam. In particular, the variation along the beam of the effective second moment of area I of the cross-section is needed to determine the deflections of the beam, and to determine the moments and shears when the beam is statically indeterminate. For this purpose, local variations in the cross-section, such as those due to bolt holes, may be ignored. The bending moments and shear forces in statically determinate beams can be determined by making use of the principles of static equilibrium. The deflections of beams can also be determined accurately by using many methods, but it is often sufficient to use approximate estimates for comparison with the desirable maximum values. Thus, in simply supported, it is usually accurate enough to use the mid-span deflection, like this figure. The mid-span deflection WC measured relative to the level of the left-hand support depends on the distribution of the applied load, the end moments Ma and Mb taken as clockwise positive, and the sinking Wab of the right-hand support below the left-hand support, and can be expressed as this equation. In this equation, the deflections Wc and Wab are expressed in millimeter. The moments Ms, Ma, Mb are in kilonewton meter. The span L is in meter, and the second moment of area I is in centimeter power 4. Expressions for the simple beam moments Ms and the values of the coefficients K are given in this figure for a number of loading distributions. These can be combined together to find the central deflections caused by many other loading distributions. Next, we will introduce the plastic analysis of beams. As the load on a ductile steel beam is increased, the stresses in the beam also increase until the yield stress is reached, with further increases in the load. Yielding spreads through the most highly strained cross-section of the beam until it becomes fully plastic at the moment MP. At this stage, the section forms a plastic hinge which allows the beam segments on either side to rotate freely under the moment MP. If the beam was originally statically determinate, this plastic hinge reduces it to a mechanism and prevents it from supporting any additional load. At high moment curvatures, the limiting situation is approached for which the beam section is completely yielded at the fully plastic moment MP equal to Fy times WPL, where Fy is the yield stress, WPL is the plastic section modulus. The approximate approach of the moment curvature relationship shown in Figure C to the fully plastic limit forms the basis of the simple rigid plastic assumption for which the basic stress-strain relationship is replaced by the dashed line in Figure B. Thus, elastic strength completely ignores the curvature of any elastic and elastic plastic regions, m less than mp, and assumes that the curvature becomes infinite at any point where m equal to mp. The consequences of the rigid plastic assumption on the theoretical behavior, if a simply supported beam with a central concentrated load, are shown in these figures. In the real beam shown in Figure B, there is a finite length of the beam which is elastic plastic, and in which the curvatures are large, while the remaining portions are elastic and have small curvatures. However, according to the rigid plastic assumption, the curvature becomes infinite at mid-span when this section becomes fully plastic, m equal to mp, while the two halves of the beam have zero curvature and remain straight, as shown in Figure C. The infinite curvature at the point of fully plasticity and the finite slope change theta predicted by the rigid plastic assumption lead to the plastic hinge concept illustrated in Figure B. The plastic hinge can assume any slope change theta once the full plastic moment mp has been reached. This behavior is contrasted with that shown in Figure C for a frictionless hinge, which can assume any slope change theta at zero moment. It should be noted that when the full plastic moment mp of the simply supported beam shown in Figure A is reached, the rigid plastic assumption predicts that a two-bar mechanism will be formed by the plastic hinge and the two frictionless support hinges, and that the beam will deform freely without any further increase in load. Thus, the ultimate load of the beam is QULT equal to 4 times mp over L, which reduces the beam to a plastic collapse mechanism. From conclusions, what have we learned? An elastic analysis is also required to determine the deflections of the beam, so that this can be compared with the desirable limiting values. In the plastic analysis of beams, the mechanism condition is investigated to determine the ultimate strength. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,